right, we're talking about buffers here today, page 666 in your textbook. Buffers and buffered solutions. We're going to talk about what is a buffer, why are buffers helpful for us, where do we see them in nature, and just talk a little bit about some questions regarding buffers. So many fluids in your body must be maintained within a very narrow pH range to remain healthy. Okay, this is something that's not really, we don't think about this every day, but the pH of our blood, the pH of the fluids in our tissues and stuff, if we get wildly acidic or wildly basic, we are in big trouble. So a wonderful design feature in our body is a buffer system that can absorb moderate amounts of acids or bases without significantly changing the pH, or without significant change in pH. So this is like I said, a wonderful design feature that we benefit from in our bodies. If something goes haywire, something we eat, something our body overproduces because of a stress in health or the environment or whatever, we actually have chemicals in our blood and in our system that can act as a buffer. So the word buffer, I mean, if we just kind of go back to the word buffer, a buffer zone or a buffer period or a buffer, that's sort of something that can absorb something unexpected or a little bit extra. When I'm planning my lessons, sometimes I will plan a buffer class or a buffer period where if we get behind, we can catch up, right? So that's kind of a buffer. If, you wear a windbreaker to buffer the wind, okay? To kind of be that barrier, that protection, that absorption. You wear a heavy coat when it's cold outside to insulate yourself, but that's the buffer. That's between you and the harsh elements. So there's this bit of a safe zone. That's kind of the meaning of buffers, what we're going to use here. A buffer system, now this is how it works. It supplies ions that can react both with the hydronium and the hydroxide ions. So very, very cool. We have ions in our bodies that can take on an excess of hydrogen ions or an excess of hydroxide ions to stabilize the pH in our system. Since these free ions are neutralized, the pH is relatively unaffected. Blood is buffered principally by the hydrogen carbonate ion. Hydrogen carbonate ion. Now I'm going to highlight, I guess, some of these. These are the ones, if you have blank notes in front of you, I think these highlighted ones are the words you need to put in there. So hydrogen carbonate ion, that's HCO3 minus 1, is a buffer. So look at what happens here. And again, on your notes, I'm not sure exactly what you have to fill in at this point, but if we have hydrogen carbonate ion and there is a presence or an overpresence of hydronium ion, this is what happens. The hydronium ion, obviously this is an acid, it will donate a proton, and guess what? HCO3 minus becomes H2CO3. And this acid turns into water. Okay? Now this H2CO3, okay, I don't know if they, okay, so when, yeah, all right. So this is basically, this is more of a neutral compound, right? This is neutral. So this is not acidic or basic, neither is water. So it takes this acid sort of threat and it neutralizes it, okay? So what happens if a hydrogen carbonate comes into presence with an overproduction of hydroxide ions, making the blood or whatever basic, okay, too basic? Well, what happens is it leaps into action as well. And this H right here, so you notice it can accept an H, no problem. It can also donate this H. That's amazing. And we have a carbonate ion, and of course the OH becomes water. So again, the threat of the overproduction of hydroxide ions or the basic solution there is neutralized. So we have water in both cases. Hydroxide ion is eliminated in the second one. So hydronium ion is eliminated here, neutralizing our low pH, and the hydroxide ion is eliminated here. When hydrogen carbonate reaches the lungs, so if, let's say, what happens if it's not needed? Well, it breaks down in the lungs, decomposes to CO2, which is then exhaled. That's amazing. So great. So we have this system in our body where there's these chemicals that are ready to protect wild changes in pH. And guess what? If they're not needed, if they're not used, they just kind of slowly die this disintegrated death, and they're exhaled. And every breath we should be thanking these CO2 molecules that were once hydrogen carbonate. Thank you for stabilizing the pH in our blood, but we don't do that, do we? We don't thank every breath that we breathe out. But anyways, so stuff's happening in our body that's amazing that we don't even really think about. So that's an example of a buffer system. When hydrogen carbonate reaches the lungs, I read that already, fine. This is the one I want, dihydrogen phosphate. Okay, dihydrogen phosphate. Now this is carbonate, so phosphate would be the PO4, H2PO4. It also acts as a buffer system, a buffer in the blood as well. Okay, so we also have another ion that's ready to go to battle these pH changes. Okay, that's the basic explanation of what a buffer system is and how our body uses these chemicals to stabilize pH. There are some questions in the text that I think would go well with this lesson, so I'm going to encourage you to do these questions as well. Page 668 is where you find these. Number 51 says, compare the results of two experiments. First, a small amount of base is added to an unbuffered solution with a pH of 7. Second, the same amount of base is added to a buffered solution with a pH of 7. So what's going to happen if base is added to an unbuffered solution versus a buffered solution? This is a pretty straightforward question. Tell me what's going to happen in these solutions. Will the pH change? Will there be some ions that will be remaining in solution? There's some ions that will be reacted with some kind of buffer or what? So just a quick explanation of what you think should happen here. And number 52 says this: calculate the molarity of a solution of hydrobromic acid, that's HBr, if 30 mils of 0.1 molar NaOH is required to titrate 25 mils of the acid to the equivalence point. And equivalence point is going to be a pH of 7 there. Okay, so where they're completely neutralized, with an equal number of moles of each. So as we did in the last lesson there that we just did, you're going to have to write out this equation, see if the reactants are 1-to-1 ratio or not. That's going to be important. Then you can use your C1V1, C2V2 probably to find this out here. I'll figure this one out. Okay? Any questions about buffers? Okay. Go ahead and work on these questions there, and then I'll show you some solutions there in a little bit. Okay, so there's some sample answers for number 51. Obviously, the pH is going to change in an unbuffered solution, whereas the pH will change very little in a buffered solution. The OH ions in the unbuffered solutions will not react with anything and therefore cause the pH to rise because of the excess OH minus ions. And in the buffered solution, these OH minus ions that would be produced in the solution by the base will react with the compound, whatever it is, in the buffered solution, converting the OH minus to H2O. So this would be a good full detailed response here for 51. So for number 52, the equation is a 1-to-1, and you're going to use C1V1 equals C2V2, no problem. And here's your solution.